Yes. So thank you very much to the Boehmich Institute for hosting this extremely nice conference and for the opportunity to speak. It's really an honor. So today I'm going to be telling you about a kind of comparatively very young subfield of QCD, which goes under the name of jet substructure. And so this is something which has really emerged in the last kind of decade or so with the advent of the LHC. And so despite being kind of a very young field, I think it's really given some qualitatively new ways to study the dynamics of QCD at colliders, both theoretically and experimentally, as was highlighted in Barbara's very nice talk. And so I should warn in advance that I have zero interesting stories about the history of QCD. And so instead, I'm going to try and make up for that by showing some very recent experimental results, so some actually just from the last week, which I think really illustrate the kind of vibrancy of QCD at 50 years in. OK, so as has already been highlighted many times throughout this conference, due to asymptotic freedom, jets play a kind of central role in colliders as the proxies for the underlying quarks and gluons. And so this is kind of from these famous three-jet events from quite a long time ago. And so one can really think of these jets as the long-distance manifestation of the underlying microscopic interactions of the quarks and gluons as shown down here. And so these jets have kind of, let's say, a few GeV energy and a handful, for example, for this one, 4 particles. And so for my entire career, the kind of jets that have been around have been essentially this scaled up by a factor of 1,000. So these are jets at the LHC. So this is a kind of dijet event at 3.2 TeV. So this is almost exactly a factor 1,000 scaled up compared to the previous one. And you also get these spectacular kind of extremely high multiplicity events. And so this really provides kind of a very rich data set for exploring the dynamics of QCD. And so one thing you might think is that once you reach kind of sufficiently high energies, everything is just asymptotically free, and so these jets kind of just evolve maybe logarithmically, but you don't get anything qualitatively new. But of course, this isn't true because in addition to just QCD, you have the standard model. And so in particular, you have the electroweak scale as a kind of real new scale. And so the LHC is the first collider where you really have particles which were previously considered to be very heavy. So for example, the Higgs boson or the top quark. And so where you used to be able to just be able to produce these at rest, you can now produce these with very high boosts. So for example, you can produce top quarks with TeV scale energies. And so these decay into jets, which imprint the kind of dynamics, for example, in this case, of this top quark, into a very complicated substructure of the jets. And so what you really have at the LHC is that all the dynamics of the electroweak scale are imprinted in detailed ways into the energy flow within the jets. And so while earlier on, jets were the kind of long-distance manifestation just of quarks and gluons, now jets are essentially the long-distance manifestation of all the standard model dynamics. So for example, you have these Higgses, all the gauge bosons, all the quarks and gluons. And so if you really want to understand or kind of make the most out of the rich collider data set that we have, you really need to understand QCD jets in detail. And in particular, the very detailed substructure of these jets. And so understanding QCD jets really took on a central role motivated by this kind of new phenomena of boosted electroweak scale particles. And so, of course, understanding jets has a very long and rich history, but this really kind of changed qualitatively in about 2008 with 2 particular works. So one was the introduction of the anti-KT jet clustering algorithm by Cacciari, Salam, and Gregory Soyer, which gave rise to kind of a robust or an experimentally robust and theoretically calculable way of studying jets in hadron colliders. And using this, they proposed to use the internal substructure of jets as a new way of searching for the Higgs boson, so a specific case of which I showed earlier. And so this proposal really had kind of a tremendous influence, particularly on people of, let's say, my generation, of reinvigorating the kind of study of jets as objects in their own right, and also perhaps interesting people who are not previously studying QCD, that understanding the detailed dynamics of QCD can really have an impact for example, searching for beyond the standard model physics or studying the Higgs boson. And so it really had a kind of tremendous influence, as has been seen by this huge number of citations. And so since then, jet substructure has really kind of emerged as a central new technique at the LHC. And so it's gone beyond just providing these kind of innovative search techniques. to really be developing new ways of probing QCD dynamics. Because once you start looking inside these jets, you can then kind of move beyond your original motivations of studying these new particles to just providing new ways of studying QCD itself. So for example, one that I'll talk about is kind of imaging the confinement transition. And it really kind of allows you a whole host of new techniques to understand QCD in much more detailed ways. And so because of this, jet substructure has kind of evolved beyond its origin to have a huge impact on beyond the standard model physics, high energy QCD, and what is typically termed nuclear physics or heavy ion experiments. And so in this talk, what I'm going to try and do is give an overview of some of the kind of recent developments in jet substructure. And since we've already had extremely nice reviews of effective field theory techniques and perturbative calculations and parton showers, I'm going to focus mostly on the kind of observables or the jet substructure aspect and a little bit less on how these were actually calculated, although I'd be happy to discuss kind of those aspects after. And so the kind of general outlines, I first want to go through a little bit just about how one actually talks about kind of measuring this energy flux and what type of observables one wants to study, and a little bit about the history of these observables. Then I'm going to focus first on the case of just standard or massless quarks and gluons, or QCD by itself, and show how we can use these observables to kind of identify very nice, for example, scaling behaviors of quarks and gluons in these very, very high energy jets, which we have previously not been able to measure. And then I'll apply this to more complicated cases where you have these additional scales, for example, these intrinsic scales in the standard model, or emergent scales like the hadronization scale or scales in the quark-gluon plasma. Okay. So one thing which came out of trying to better understand how to ask questions, for example, is there a Higgs boson produced in here, is just to try and re-understand how to interpret events in QCD with extremely high multiplicity. So how do you ask questions about these very complicated events in a way which you can answer in perturbation theory, or which you can understand from a kind of first principles theoretical perspective? So it's kind of how do you ask questions in these high multiplicity events? And so, for example, in condensed matter physics or in cosmology, we understand very well how to do this. And in particular, we decode the kind of underlying dynamics using correlation functions measured at some fixed time slice. And so the reason why we do this is, of course, for example, if you measure a 2-point correlation function, it introduces some particular scale. And so you get out these kind of famous plots where you can identify the underlying dynamics as a function of the scale. And so this really allows you to kind of see what is happening as a function of scale. And so if one looks at these collider events, so for example, this one from STAR, particularly if it's kind of colored in the same way, these are kind of a very similar picture where you want to understand how to go from the kind of asymptotic or kind of macroscopic energy flux back to the underlying microscopic dynamics which created that. And so what one wants to kind of understand is what is the analog of these very nice correlation functions that we can understand in collider physics. And so this is something which has an extremely long history, and in particular, some of it I actually just learned from George Sturman's talk. So one thing that was found kind of very early on is that the expectation value of energy flux at specific angles, so this was originally in this paper from 1975, termed the angular energy current. So this is something which is computable purely in perturbation theory. And as was said in his talk, he had this very nice statement that since then, energy flow has kind of become the focus of computability in perturbative QCD. And so this is something which has kind of evolved considerably over time. In particular, the introduction of kind of operator versions of these equalities, or of this operator by Korchemsky and Sturman. And also a whole bunch of work by Korchemsky and his collaborators Sakachev and Zhibodev of really developing these operators in n=4 super Yang-Mills. But kind of what this gave us, in particular, these kind of IRC-safe observables, is a kind of safe starting point of what observables to explore in QCD. So later on, I'll kind of evolve beyond this. But what this gave us is a kind of a set of observables which you can really understand in fixed order perturbation theory. So the kind of modern version of this question, which has seen a resurgence of interest, is in thinking about how to understand this problem just from a formal field theory perspective. And so the way that one wants to kind of think about this is to just kind of ask, when you have these kind of very impressive detectors, what are you actually doing from a field theory perspective? And another way of saying this is kind of what is a detector in field theory? And so there's this nice illustration made by David Simmons-Duffin, where kind of what you're doing in these colliders is you're hitting things with a hammer. And so we all learn, particularly for example in E plus E minus, you're really pinging the system with some, you can expand it over some local operators. And so then these excitations propagate out to infinity, and you want to kind of image them or detect them with some cameras. And so what one wants to learn how to do, if you want to really understand from first principles theory what you're doing for these observables, is to learn how to write these camera or so-called detector operators as also sums over operators in the field theory and kind of understand what detectors exist in your field theory. And as I said, this for the particular case of calorimeter cells, this was this particular definition shown here, but this can be generalized to other detectors. And so the difference as compared to local operators is these are particular light ray operators because you're absorbing or you're kind of measuring the energy flux and you have to integrate over all times. And so the very nice aspect of this is it gives a kind of very precise definition of the observables that you would like to study in a kind of field theory perspective. And it provides a very sharp link between what you can measure experimentally and the underlying kind of field theory object. So this is something which can be studied, for example, by a formal theorist or actually measured in the experiment. And so it really kind of builds a bridge between those two different worlds. And so this is actually, or the study of these correlations is something which was proposed about 45 years ago now, which is the kind of first attempt at jet substructure, in particular by Basham, Brown, Ellis, and Love. And I'll highlight in particular Stephen Ellis, both in his younger and older form, because both for kind of introducing these energy correlation functions as well as for a large number of other contributions for studying jets in hadron colliders. And so as you can see from this plot shown here, which also coincidentally looks exactly like the measurement of the energy correlators in E plus E minus, there's been a huge kind of resurgence of interest in these observables, in particular in the last just 1 or 2 years, so it's kind of a very recent thing. And this is largely due, so both due to very impressive improvements in our ability to perform calculations in perturbative QCDs, so we can now actually compute these things and study how they behave, as well as due to the extraordinary LHC dataset, where we can really measure these things in extremely perturbative regimes. And so just again to kind of really emphasize why the LHC makes a huge difference here. So this is this picture of these jets, I guess at Tasso. And so if you want to measure, for example, a 4-point correlation function, if you only have 4 particles in your jet, this is not going to go very well. And so you're kind of in the regime, or here is it kind of in the middle, but you're in the regime essentially of kind of exclusive amplitudes. Whereas as you go to the TeV scale, so you essentially scale this up by a factor of 1,000, you now really have these extraordinarily high multiplicity events. And so you really have to learn how to talk about it in a kind of very different way. And so you're kind of moving from these exclusive amplitudes really to the study of correlations in very high multiplicity states. And so apart from its interest just for looking, for example, for Higgs bosons, et cetera, this is really a new kind of regime of QCD which has not been explored kind of experimentally prior to the LHC. And so the kind of present form of these energy correlators, which I'll go through in the rest of the talk, really allow one to kind of image the structure of the kind of transition between quarks and gluons into hadrons. And so I'll explain the different parts of this plot as I go through. But so this is a measurement of this 2-point energy correlation function as a function of the angle between these two calorimeter cells. And so at large angles, this is something which is calculable in perturbative QCD. And so what you get is this scaling behavior, which is shown here, which is the scaling behavior, or it's a non-integer scaling behavior with an exponent which can be calculated in perturbation theory. And so it's really the interacting quarks and gluons which give rise to this non-integer scaling and to non-trivial higher point correlation functions. So if you measure kind of 3-point and higher, there'll be non-trivial manifestation of the interactions of quarks and gluons. Then you have this very abrupt transition where the scaling behavior stops and you see that confinement occurs. And then on this side, what you have are just freely propagating hadrons with an integer scaling law, which is just geometric from the many hadrons being there, and all trivial higher point correlation functions. And so because of this kind of exceptional angular resolution, as well as the very high energy, you can kind of really image this inside high energy jets at the LHC and see very nicely, for example, in this case, both asymptotic freedom and confinement in kind of one single plot. And so it kind of really allows you a new way of looking at QCD. Okay, so now what I want to do is to focus on the kind of first part of this, and then I'll discuss the hadronization. And so the first part is really this asymptotic scaling of very high energy quarks and gluons inside these jets. So scaling behavior is something which has an extremely long history in quantum field theory. And so in particular, in the Euclidean regime, it's very well understood through the operator product expansion. So as you move two operators together with a Euclidean distance, you get some very nice scaling behavior as a function of that separation with some angular exponent, which you can, or you could compute, for example, in perturbation theory, or you could measure it directly from some scaling behavior in experiment. And so this is something which was crucial in the development, for example, of E plus E minus or DIS. But when we go to jets, you're in a very different regime. So you're no longer in this Euclidean regime, and instead you're really studying kind of very Lorentzian physics of these light ray operators. So one of the things which is extremely interesting, and which came out originally from this work of Hoffman and Maldacena, is that these so-called light ray or detector operators also admit an operator product expansion as you bring them together. And so you can think of this either as literally bringing two calorimeter cells together in your detector, or in the more kind of space-time picture, you're bringing these two line operators together as a function of the angle on the celestial sphere. And so what one can show, and I again won't go through the details, is that this also admits an OPE onto another particular, or another operator whose exact form doesn't matter, but it predicts an angular scaling shown here with certain anomalous dimensions, just like in the case of local operators. And so what this does is to predict that at high energies, where you can perform perturbative calculations, you get a very nice power law scaling in the correlations of the energy flux as you scan the calorimeters, or the kind of angular separation between the calorimeters. And so one nice thing which one can just do is now, using this very nice high energy data, you can go in and actually just measure this. So this is a first kind of preliminary example of this using some open data that we did. And you can see in dots are the actual data in a real fully messy Hadron Collider environment. And you see that they exhibit this kind of beautiful power law scaling shown here, which is compared against perturbative calculations. And you really see this beautiful scaling behavior and energy flux even in this very complicated environment. And so this is really kind of a prediction of quantum field theory in general, which is now being able to be verified using these very high energy jets and these very high multiplicity states. So one thing which actually just came out last week is this has now been measured across a huge variety of experiments, so in particular ALICE, CMS, and STAR, and all kind of combined onto this plot, where they've measured this two-point correlation function all the way from 15 GeV, which I guess is STAR, up to about 2 TeV. So these are for extremely high energy jets. And you can see that all of these, and again, I apologize, this is now a logarithmic plot, but you can see, for example, particularly at very high energies, you get this beautiful power law scaling over many orders of magnitude and angle. And so this is really kind of measuring precisely this nice scaling behavior predicted by the operator product expansion. And so in these plots, this is dominated by the kind of classical part of the scaling. So it goes almost like this kind of like 1 over the theta. But one thing which is extremely nice about these very precise colliders is we can actually do much better and actually really kind of pin down the anomalous scaling predicted by this operator product expansion. And so one thing which is quite neat about this operator product expansion is it makes a prediction for the scaling of generic endpoint functions. So much like just for correlation functions of local operators, as you scale them as a function of size, you expect them to have some particular anomalous dimension which characterizes that scaling. And so one thing which one can do is one can consider higher point correlation functions. So in this picture, it's a 3-point correlation function, and you can normalize it to this 2-point correlation function. And so what this does is to remove the kind of classical part of the scaling and give rise to a scaling which is a difference of anomalous dimensions. So for people that are more experts in this area, it's the difference of the twist 2 operators for different values of the spin. And so if you measure this, what you really see is as you take these ratios, for example, this is the 3-point over 2-point, 4-point over 2-point, 5-point over 2-point, and 6-point over 2-point. Each of these has this nice scaling behavior, which is dictated by this difference of anomalous dimensions. And so by measuring this kind of scaling behavior of this asymptotic energy flux, you're really able to kind of probe the spectrum of anomalous dimensions which are characterizing the underlying field theory. And so again, if there weren't kind of quantum corrections, these would just be flat. And so this is purely the kind of anomalous dimension in the field theory. And so again, this is something that was very recently measured from 15 GeV all the way up to 2 TeV. And so in particular, what was measured is this ratio of the 3-point correlator to the 2-point correlator shown down here, which is scale like the difference of the twist 2 spin 4 and twist 2 spin 3 operators. And so what you see in all these plots is this very nice scaling behavior shown as a function of these different values of the PT. And so you can really see this kind of beautiful power law scaling, which is just as a function of these particular anomalous dimensions of the field theory, which in particular depend on the coupling. And so this is done all the way from down here at, let's say, 60 GeV, all the way up to about 2 TeV. And so in a conformal field theory, you get the exact same slope for all values of the, all values of the energy. And so one thing which is quite neat, and since this is supposed to be the kind of 50th birthday of asymptotic freedom, is you can just read off the slope by I. So in particular, that it gets more and more steep as you go to lower values of the energy, and it gets correspondingly flat as you go to higher values. And so if you plot the value of this slope, you can see this nice kind of behavior of asymptotic freedom, where the slope gets mellower and mellower as you go out. And so that's just because the critical exponent depends on the value of alpha s, which runs with PT. And so you can really see this kind of asymptotic freedom very nicely just by eye from measuring these jet substructure observables. And so, of course, one other thing which you can do, which really exploits these very high energy jets, is that from this exponent, so this is just like you would do, for example, if you wanted to measure a critical exponent, you can measure this critical exponent or the scaling precisely in the experiment, and then you can use it to extract the value of the strong coupling, which just dictates the particular slope. And so this was done, I guess, a couple weeks ago now by the CMS collaboration, and you can extract from this a relatively competitive value of alpha s with a kind of 4% accuracy. And so this is kind of a first illustration that you can really get kind of quantitative things out of jet substructure, and it's really providing you kind of a qualitative new way of extracting, for example, values of or parameters of QCD. And so this is still not quite kind of fully competitive with, there's kind of results at order 1%, but it's kind of an illustration that this can be done in the very complicated LHC environment, and then one can hope to improve it and one can definitely add higher order perturbative corrections to really exploit the very high energies of the LHC and allow kind of new ways of extracting parameters such as the strong coupling. So this is just moved to the running, to very high orders, and so this is just moved to MZ. Well, the measurement is done across all these values of PT. And yeah. And so it's more complicated because as a function of the angle, you're probing slightly different scales, but you know how to run the value of alpha s extremely well, and so then it's just converted to a value at MZ. But it allows you to probe it over this wide range of scales, which is why, for example, you're able to see kind of cleanly asymptotic freedom from this. OK. And so I should just say that I skipped through kind of many of the underlying ways in which these are computed. And so I also wanted to highlight that any kind of quantitative result at colliders really relies kind of very crucially on these kind of seminal results of Collins, Soper, and Sturman of these factorization proofs, which enable these actual quantitative calculations of the value of the strong coupling, and which were greatly extended, so with the soft collinear effective theory, from these very simple processes, for example, beta Ks, to much more complicated processes really involving all these jet clustering algorithms and stuff, all of which went into these calculations, but I've kind of pushed under the rug to emphasize this scaling behavior. And so these really form the kind of backbone of being able to produce kind of actual quantitative theoretical predictions of these observables in the complicated LHC environment. OK, so now, as I mentioned earlier, you can use this as you go to smaller angular scales to image the confinement transition. So at very large scales, you can compute in perturbative QCD. And then what you expect is that at some scale, you have an abrupt transition due to confinement. Oops. Sorry. And so you expect that you have this very nice scaling behavior when you're at angles where you're accessing the interactions of the quarks and gluons. And then you expect to have this really abrupt transition to just free scaling hadrons. And so one of the neat things is that this can actually, as I illustrated earlier, just be directly measured inside these high energy jets. And so it really gives you a kind of experimental insight into the dynamics of the confinement process, which then hopefully you can learn to better understand what is actually going on. And so now this plot will hopefully make a little bit more sense. And so on this right-hand side, you have this very nice asymptotic scaling coming from the underlying interacting quarks and gluons. And then you can just directly see that this breaks at some particular confinement scale. And if converted, depending on the energy, this converts just to lambda QCD. And then on this side, you get a very different scaling behavior, which is just associated with freely interacting hadrons going out into your detector. So on this side, it's kind of trivial. It's just a geometric property of a bunch of uniformly distributed hadrons. And so you can really see the kind of rearrangement of the degrees of freedom as a function of scale. And in particular, kind of experimental measurements in this region where we don't currently have ways to compute can provide new insight both into parton shower generators as well as hopefully analytic understandings of the confinement process.
Can you turn that power into an energy scale?
Yeah, you just multiply by the PT of the jet.
So what is it?
Well, this is about like 2 GeV. Yeah, 2.4. Yeah. Okay, so one thing which one can do, so this is kind of a very nice scaling behavior, but it's in some sense the simplest property which one can study of QCD. And so of course one would like to kind of go beyond just these simple 2-point correlation functions. So 2-point correlation functions kind of identify a scale, and then what you want to do is to measure kind of higher point correlation functions to understand the underlying dynamics. And so this is, of course, something which has been done for a long time, for example, in cosmology, where people compute higher point correlation functions to really probe the structure of, for example, inflation. And so what we would like to do is to extend this to the case of collider physics and to compute higher point correlation functions. And surprisingly, this is something where there have been relatively little, so there's been spectacular developments in perturbative calculations of amplitudes, but there's been much less progress in understanding these kind of energy correlator style observables. And so again, to kind of skip through the actual calculations, but using these kind of modern amplitude techniques, this is something which can be done relatively straightforwardly. And one can compute, for example, the 3-point correlator shown here. And so this is a comparison of the kind of analytic result in QCD versus what is measured inside a high-energy jet at the LHC. And so you can really measure the structure of these higher point correlation functions. And so this is something which is a bit harder to understand kind of by eye. So this is a plot as a function of the shape of this triangle. So in the back is this kind of equilateral triangle. Down here is what is referred to as this kind of flattened triangle. And over here is this kind of squeezed triangle. And so what it really shows is you kind of have, at least at very high energies, you have kind of theoretical control over these multi-point correlation functions inside jets using perturbative QCD. And so this is something which is really only possible inside these extremely high-energy jets and which could not be done before the LHC. Sorry, this seems to maybe... Oops. Okay, sorry. Okay, sorry. Now it's back. Okay, and so that's hopefully convinced you that now we've developed these very nice tools for studying kind of energy flux. And this is something which is based purely on perturbation theory and the extremely high energies of the LHC. But of course, one thing one would like to do is to kind of go beyond this energy flux paradigm, which was originally highlighted by George Sturman. And so, of course, the kind of reason for doing this is very obvious. So if you want to better understand the hadronization process, it's kind of an inconvenience that energy flux is by definition insensitive to many of the properties which characterize this hadronization process. So for example, one would like to track how like charge or flavor kind of go through this process and are correlated amongst the final state hadrons. And so this is something which cannot be computed purely in perturbation theory. And so one thing one would like to understand is how far one can kind of start moving away from these very nice IRC-safe observables by starting to incorporate other properties such as charge. So obviously you cannot go fully and compute every property of hadrons, but one would like to see how far you can kind of deform away from this nice starting point to start to understand properties of the transition from quarks and gluons into hadrons. Whoa. Oh. Okay, sorry about that. Okay. I think now, yeah, someone wrote something, but yeah. Okay, so one thing, so these are not computable purely within perturbation theory, but kind of one way of attacking this program or of attacking this problem is by combining perturbative calculations with factorization theorems and the renormalization group. And so one way of characterizing these processes is to introduce universal matrix elements which describe the fragmentation process. And so, of course, the most famous of these are the standard fragmentation functions, which evolve using the DGLAP evolution. But to compute more complicated correlations, you need kind of extensions of these, which are kind of multi-hadron fragmentation functions, similar to what was discussed for the space-like case in Korchemsky's talk. And so this is something where there's really been a huge amount of progress just in understanding the structure of the renormalization group evolution of these functions. So unfortunately, I don't have time to go into detail, but these exhibit kind of very interesting renormalization group flows and characterize the correlations in the hadronization process. And so the upshot of this is you can kind of use the universality of these functions and the renormalization group to understand more complicated correlation functions. And in particular, what you can start to understand are, for example, correlations on the energy flux carried by hadrons of specific quantum numbers. So for example, you can try and understand how the energy flux in positive particles is correlated with the energy flux in negative particles. And you start to look how electromagnetic charge is correlated amongst final state hadrons. And so if you do this, you can compute, for example, what is shown here in blue is the correlation between positive and negative charged energy flux. And in red is between same sign hadrons. And so what you can see is that you predict slightly different scaling behaviors, which are dictated by the renormalization group, which show, for example, enhanced correlations between positive and negative, or between opposite charged hadrons at small angles as compared to same sign hadrons. And so this is just something which comes out of the renormalization group. And so this is not something of electromagnetic nature. This is just something which is generated by hadronization. And so hopefully this can allow one to understand, for example, properties of the string or cluster models of hadronization. And so one question which is kind of obvious from this perspective is kind of how far can one push into the confinement transition by combining modern perturbative techniques and the renormalization group. And one thing that would be very important is kind of experimental measurements of these more complicated correlations. This thing, sorry, keeps going. Sorry about that. Okay, so hopefully I've convinced you, at least for the study of pure kind of QCD, in the last kind of decade, there's been a tremendous progress in what we can calculate inside high-energy jets at the LHC. And so for me, this has been kind of really neat because there's been a rapid evolution of these techniques from the theory side all the way to kind of real experimental measurements now of actual quantities, which give new ways of kind of understanding the real world at colliders from neat new theory insights. And so this has so far just been for trying to understand at the base level these quantum or QCD jets. But now what we want to really do is to go back to the kind of original goal of jet substructure, which is to use these as kind of calibrated probes of more complicated systems. Okay, and so what I wanted to do is just very briefly go through kind of 3 examples, and I'll just give, especially for time, a brief summary of each, of trying to use jet substructure in more complicated cases. So one will be for doing precision standard model measurements. One will be a kind of nuclear physics example of understanding the quark-gluon plasma, and one will be looking for kind of new particles and interactions in the standard model. Okay, so the first thing one can try and do with this is to look more in detail at standard model processes. So in the absence of any new physics, the kind of best thing we can do is to really measure the properties of the standard model in extreme detail. And so one of the obvious targets is the top quark mass. And so this is something which is very important for example, electroweak vacuum stability. But its precision extraction from experiment is, or really requires a detailed understanding of QCD. And so because of the LHC, you have these very large samples of highly boosted top quarks. You can measure these energy correlators on them to try and extract the values of the mass. And so in particular, because of this kind of three-body decay, they'll imprint themselves in these correlators. So if I plot, for example, this correlator which I showed before, just as a function of the overall size, you'll get this very steep scaling, which is the power law I showed before at low masses. Then you get a peak at the value of the W mass, and then a peak at the value of the top mass. And so you can really just see these imprinted in, and in particular, because you know the value of the W mass, this gives kind of a standard candle for converting between these angles and masses. And more generally than this, because we also know how to compute the full shape dependence of higher point correlation functions, you can actually measure the full shape dependence. And so this is very much like in cosmology, where, for example, you'll have some structure which imprints into an equilateral, which is given by the kind of original decay of the top quark. And then you can also have this kind of long on-shell propagation of the W, which sets an additional scale. And so you can really kind of read off in the shape of this the values of the W and the top mass. And so hopefully this will give a kind of competitive way of extracting the top quark mass using jet substructure. So the second example of putting things into a more complicated system is to put things into the quark-gluon plasma, as was very nicely discussed in a number of talks earlier this week. And so again, the way that one wants to do this is to try and shoot jets through the system and to measure from its asymptotic properties of the underlying field theory. And in particular, because this is an extraordinarily complicated QCD system, it's a kind of primary target for these new jet substructure techniques. And it's a very nice place to apply them. And so the way we kind of do this is we can imagine in this very toy setup that we can just take a quark and shoot it through, for example, some plasma that has a fixed size. So in the real world, this will be more complicated. And then we can try and see how the presence of this scale, which is about kind of 10 Fermi, imprints itself into the correlation functions in your jet. And so the most basic question one can ask is just how do you see, for example, that there's some kind of tiny little ball of plasma in the center of your collision. So the very neat thing, and so these are just calculations, so the hope is that it will be measured very soon. But if you measure this correlation function as a function of the angle between these two detectors, so when you're at very small angles, this parton lives for a very long amount of time and just kind of shoots out of the plasma without seeing it. And so you get this nice power law scaling, which I discussed kind of earlier, and which is reflective of the asymptotically free quarks and gluons. But then as you pull these apart, you kind of force the interaction back into the plasma. And so at the scale of the size of the plasma, you see this abrupt transition where you kind of image the presence of the underlying plasma. And so then ideally by measuring, for example, higher point correlation functions or the detailed value of the shape, you can extract values, for example, of the transport coefficients, et cetera, and really understand the microscopic dynamics of the underlying plasma. And so this is something which is being measured and will hopefully be available publicly soon. And so the final examples which I want to give are just a couple quick examples of how this very nice understanding of QCD can be used to look for new particles and interactions at the LHC, as was the kind of original goal of jet substructure. And so this has had a kind of tremendous impact on BSM searches. So there's literally kind of hundreds of these, because for every particular BSM scenario, it will imprint itself in the energy flux in some particular way. And so since there has been no discovery of beyond the standard model physics, instead I'll discuss the impact of this on Higgs searches. And so this is something where there's been a kind of a variety of new Higgs searches which have been enabled by these techniques, which I think are quite neat. So the first thing one can do is to try and look for decays of the Higgs into charm quarks to probe the charm Yukawa. And so this is something which is extremely difficult to do. But you can do it by searching for highly boosted Higgses which decay into charm quarks in a particular jet. And so again, you identify these, and you can put the current most stringent bounds on the value of the charm Yukawa, which are given up here. And the thing which is most exciting is that this, using only kind of 100 inverse femtobarns, matches the original projected sensitivity with kind of 3,000 inverse femtobarns. And so it really shows that you have kind of qualitatively new insights from QCD to be able to better understand, for example, the dynamics of the Higgs. The second nice example which you can do is to try and look for the Higgs self-interaction, which gives access to the Higgs potential. And so, of course, this is something which has not been measured yet. So what you'd really like to measure is this trilinear Higgs coupling. But one actually new interaction of the standard model, which has been observed using these techniques, is the vector-vector to Higgs-Higgs coupling the standard model. So this is kind of a genuinely new interaction which had not been seen before the standard model, but which was measured using these jet substructure techniques. And so the final example before I conclude is to study very highly boosted top quarks, or sort of very highly boosted Higgs. And so this can be done in a variety of different channels, so both vector boson fusion and gluon-gluon fusion, to try and really probe the structure of the interactions between, for example, the gluons and the Higgs at very high energies to try and see if there's anything new happening there. And so this can be done across a variety of different channels. And so the current measurements, which just came out again about a month ago, show some deviations from the standard model. Although, of course, one probably does not expect this as actual new physics. But at the very least, kind of understanding what this is and providing ways to measure this will definitely involve a better understanding of QCD. And so just to conclude, so the kind of spectacular understanding of QCD, which has been developed over the past 50 or so years, is really being used to study the standard model in a huge variety of new ways at the LHC. And so jet substructure is a rapidly evolving kind of new field, and it's really starting to turn into kind of a precision science, enabling kind of quantitative new ways to study the strong force, and qualitative, particularly for understanding confinement. And hopefully with this kind of very rich experimental program, both from the high energy physics community and the nuclear physics community, we can expect many exciting developments in the next 50 years of QCD. So thank you, and happy birthday to asymptotic freedom.
Okay, questions? Thanks a lot for nice talk. Oh, okay.
I apologize if I missed it, but can you use this to distinguish something simple like gluon from quark jets?
So there's been a lot of study of this. So I didn't highlight that as much, but there's been a huge amount of study of that particular problem. And there's now, so that particular case is actually quite difficult, particularly high energies, because they're very similar. And so it's not as, it is something which is, there's been improvements on, but it's not nearly as good as, for example, for these Higgses or top quarks.
And in particular in AA collisions, where I think claiming that it's energy loss until you can differentiate.
Good. So I think that is one thing that we are interested in, particularly about this for distinguishing between energy loss and other effects, is in this, in this region, you have a very nice power law scaling. And so even if you modify the kind of quark or gluon fraction, it doesn't change the scaling by an integer amount. It just changes the anomalous dimensions. And so the fact there's a very abrupt change here by an integer amount makes it very hard to achieve this just by modifying, for example, the energies. And so we're hopeful that this gives a kind of clean way of kind of imaging and understanding the plasma that is less sensitive to those energy effects. But this is still something that definitely remains to be seen experimentally. But yeah, it's a very good question.
I have a couple points. Great talk. The Higgs at high XF, you talked about that. There's actually a spectacular effect from intrinsic charm. And it causes a dramatic increase of the charm of the Higgs production at large XF beyond 0.8
Okay.
XF. Another point is on the confinement. In my talk, I explained about light frontallography, which explains the spectroscopy of hadrons and also gives you the light front wave functions. For example, QQ bar goes to any meson. And so it really directly applies to that confinement domain that you highlighted.
And so this would be extremely great if one could compute, for example, this, sorry, I'm just going back. If one could compute, so currently we can compute on the perturbative side and on this side, and any model that could compute
Yeah.
this would be very nice.
Yeah, that excites me, and that's in fact,
Okay, well, that would be great if you could compute it. Yeah.
yeah, because it really does explain the spectroscopy. And also, in row electroproduction, the prediction that you have for QQ bar goes to rho agrees perfectly with the data for electroproduction,
Okay,
which is
okay.
just like this.
Yeah, no, that'd be very interesting.
Can I make one more point? I'm sorry, back for the Higgs, and that is the C and C bar actually have different distributions when you include the higher order diagrams in QCD, including the intrinsic. And so above, when you get to large X for the charm quark, you see a spectacular difference between C and C bar in a proton.
Okay, very interesting. Thank you.
So could you give us a little more detail on this double Higgs production and exactly what has been done?
Absolutely, yes. So let me, yeah, sorry I glossed. So I highlighted in the analytic part a particular subset of observables, which are these energy correlators, which have received a lot of theory attention. But so in this particular, so what's being done here is, so you have one way of trying to access di-Higgs is because the B decays is the largest branching fraction, you can try and go tag like the Higgs to BB and Higgs to BB on both sides. And in this particular case, this was done by a particular combination of these energy correlation functions, which is kind of a ratio of the 3-point to the 2-point correlation functions, which is supposed to identify jets with a 2-pronged substructure. And then so in these, what's being plotted, and so that kind of identifies them. And then what's being plotted in, for example, like here. So once you've identified these, you can plot the mass of these jets. And in particular, it's groomed and kind of to remove some soft radiation. And so what you see, for example, in one of these Higgs, which is, or ideally a Higgs, so what you see here is the Z, so this is about 90 GeV, so you see a very clear, you're finding the Z. And in particular, you can find both the Z to BB and the Z to CC. And then ideally, what you will see is some kind of peak at around 120, which is coming from the Higgs. And so you first identify them, and then you can look at their masses. And so by bounding that, for example, this bump around here isn't bigger, it puts a value on the strength of this, coupling.
Are you saying this has been done now?
So this is real data. Shown here, and so this is being done both. In this case, it's been done. So this is for the vector boson fusion as well as for gluon fusion, and you actually really kind of see it. For the di-Higgs case, you have both contributions from a variety of different sub-interactions. And so the full process comes from a combination of the actual like trilinear Higgs coupling, which is what you want, but you also have these other interactions. So in particular, this combination of these, and you also have this VV to Higgs-Higgs. And so what has been seen so far, or what is evidence for in these plots, you're able to observe the VV to Higgs-Higgs coupling, but you have not yet done it powerfully enough to see the Higgs trilinear coupling. And so that's something that will hopefully be within the high luminosity LHC. You'll really be able to identify this Higgs trilinear coupling.
And are you saying that you've distinguished between the diagram on the right and the one in the middle?
Or so what you can, this one, you have to like compute them and see the size of their effects. But if you can show that if you turn off this one, so I think this one is bigger, and so if you turn off this one, you can show that it's inconsistent. And so you can bound, so this is this value of this, they put it's called a kappa 2V, which is the value of this, and it's inconsistent if you turn this off. And so it shows that you have this particular interaction.
Okay, thank you.
Yeah, at 5 sigma or something, yeah.
Yeah, can you say a little bit about the impact of underlying event and pileup and give maybe some idea of the quantitative effects on some of the plots you've shown?
Absolutely. So one of the things which has made, or where these energy correlators are particularly nice, is because they're completely inclusive. So this is something which is very different than like in the past. If you measure like a jet shape, like the mass, this is extremely sensitive to any like, for example, soft radiation and underlying event. Whereas here, you're really measuring like a 2-point correlation, and it's energy weighted. And so for these, there's very, very little impact from the underlying event. And so in particular, sorry if I go back, these, like in these calculations, particularly once you take these ratios, so this is like not being corrected by underlying event or for anything like that, and you can really compute them precisely in perturbation theory. And so that's something where these observables are extremely well behaved, and you can add in quite large amounts of underlying event, and they have almost no effect.
And what about pileup from?
Is again that they have almost zero effect, and that's because you're focusing on just this correlation, and it's energy weighted, and so that really kills these additional effects. And so you can even do, though I didn't, or another thing you can do using these techniques shown here is you can do these on charged particles. So that's one of the things that adding these non-perturbative fragmentation functions allows one to do. And this doesn't really modify the scaling, and you can it only modifies in a way that is perturbably calculable. And so then you can do it on like charged hadrons, which even further suppresses these. And so as compared to previous things, it's a very different behavior with respect to pileup and stuff, which had previously been a big problem for jet substructure. Yes. No, this is done to, sorry, if I go back. Sorry, this thing's very confusing. So the calculation is at next to leading log. So it's actually quite, and it's for this ratio of the 3 to 2 point correlation function. And so part of this was computed with Lance Dixon, and then part of it for the 3 point was computed by these people down here, and it kind of combines a bunch of pieces. So it's actually like a next to leading calculation of both the 3 point and the 2 point, and then taking their ratio.
So for the top quark mass, the assist in that measurement for the stability of the electroweak vacuum, Ian, I think the precision we need is like 250 MeV. Do you think you could get to that precision with this assist?
I am optimistic. I mean, 250 MeV is very, very low, but I think that particularly for as David asked, it is very much less sensitive to these non-perturbative corrections and to hadronization. And so I am optimistic that it gives a new way of doing this at very high energies, which one could hope to improve. I mean, 250 MeV is optimistic, but I think it's worth trying how it can be done from jet substructure techniques. But yeah.